Hello everyone, my name is Phuc Nguyen. Today, I'm excited to present our work, Any3DIS, Class-Agnostic 3D Instant Segmentation by 2D Mask Tracking. Given a 3D point cloud and its corresponding RGBD sequence, Any3DIS generates a high-quality set of class-agnostic 3D proposals. Following recent approaches, the point cloud is then featurized or tokenized using instance-wise extraction approaches to enable support for open vocabulary and open-ended queries. Our Any3DIS achieves state-of-the-art performance on two challenging 3D indoor datasets, ScanNet 200 and ScanNet++. Compared to Open3DIS from CVPR 2024, Any3DIS not only delivers higher segmentation accuracy, but also reduces runtime by nearly 10 times, paving the way for future advancements in 3D open-world perception. Our Any3DIS consists of two main steps. Our first step, 3D-aware 2D mask tracking, incorporates geometric cues from the point cloud to improve the robustness and accuracy of 2D mask tracking across views. From a dense 3D point cloud, we apply the furthest point sampling algorithm to obtain a representative set of superpoints. For each superpoint, we compute the histogram of its projected points across all RGB images to identify a suitable pivot view. Using the camera calibration function π, we calculate the weighted distribution of each superpoint L across T views. We further incorporate contextual information from neighboring superpoints, retrieved via KNN based on the Euclidean distance between centroids, to better assess the suitability of each view as a pivot for mask tracking. We segment the pivot view using SAM2 with point-based prompts. The selected superpoint is projected onto the pivot view using camera calibration to identify its pixel region. We then apply furthest point sampling to select lambda representative pixels as prompts. SAM2 uses these to generate an accurate 2D segmentation mask of the object in its most visible view. Once the 2D mask is obtained in the pivot frame, it is used as a mask prompt to track the corresponding object across other views. We perform both forward and backward tracking from a pivot view, chosen for its representative appearance of the object. This strategy improves tracking accuracy and consistency across views. Since objects may disappear and reappear, and SAM2 forgets them after 7 frames, we introduce a training-free 3D-aware tracking mechanism to generate consistent tracklets. To maintain tracking over longer sequences, we sample projected points from the superpoint across frames and use them as additional prompts for SAM2. Overall, SAM2 receives the mask prompt from the pivot view and point prompts from other views as guidance. This allows us to generate ID-consistent 2D segmentation masks for the selected superpoint across the entire sequence. The next step involves transforming the set of 2D segmentation masks into a high-quality 3D proposal. To achieve this, we introduce a novel optimization-based technique to generate a final 3D mask proposal for each 2D mask track composed of 3D superpoints. To lift a 2D mask track into 3D, we select all superpoints whose projections significantly overlap with any 2D mask, above a predefined threshold. First, we check superpoint visibility per view using a binary visibility indicator. An initial 3D mask is formed by merging all visible superpoints. However, this naive merging can be suboptimal, as it overlooks consistency across views. A superpoint may align well in one view, but poorly in others. To improve alignment between 3D proposals and 2D masks, we refine the initial 3D mask by formulating a binary optimization problem. Select superpoints that maximize consistency with 2D segmentations across views by rewarding superpoints whose projections fall inside 2D masks and penalize those that fall outside, with the introduction of a simple yet effective dynamic programming algorithm, see Algorithm 1. Finally, tracing back with dynamic programming, we obtain the final 3D proposal for the selected superpoint. We further add this final 3D proposal to the 3D instance segmentation bank. The entire process described above is performed for a single selected superpoint. We iteratively repeat the two-step process until all superpoints are assigned. This results in a complete set of class-agnostic 3D instance segmentations. Finally, we leverage 2D foundation models like CLIP and large language models to featurize or tokenize the 3D point cloud, enabling us to assign a class name to each 3D instance mask readily for open vocabulary and open-ended queries. To evaluate the effectiveness of Any3DIS, we conduct experiments on two widely used 3D instance segmentation benchmarks, ScanNet 200 and ScanNet++. Our evaluation covers three tasks: class-agnostic 3DIS, open vocabulary 3DIS, and open-ended 3DIS. On ScanNet 200, Any3DIS is tested across 198 instance classes and achieves state-of-the-art results. The ScanNet++ dataset provides posed RGBD images along with high-quality 3D geometry captured using advanced laser scanning technology. On ScanNet++, Any3DIS achieves state-of-the-art performance on the class-agnostic benchmark, evaluated over more than 1,554 instance classes. Unlike Open3DIS, which often suffers from over-segmentation and fails to accurately group object instances, Any3DIS delivers more coherent and precise segmentations. Our Any3DIS enables powerful and flexible 3D perception for real-world applications. Starting from a 3D point cloud and a few interactive point prompts, it generates precise 3D instant segmentation masks, allowing users, such as robot operators or annotators, to efficiently label complex scenes. Furthermore, by integrating large language models, Any3DIS can provide detailed, human-readable descriptions of segmented objects, making it ideal for embodied AI systems, robot perception, AR/VR environments, and autonomous scene understanding in unstructured indoor settings. To conclude, Any3DIS achieves state-of-the-art 3D instance segmentation with superior quality and 10 times faster runtime, 488 seconds versus 4,000 seconds per scene, on two challenging indoor ScanNet datasets. Its efficiency and accuracy make it practical for real-world use and promising for future extensions like 3D Gaussian splatting. That's it. Thanks for listening.